In this video, we start subsection 3.2.4, Gaussian Elimination. At this point, we're ready to outline our first method for solving linear systems. It's called Gaussian Elimination. Given a system of linear equations, we can solve it as follows. First, we write the augmented matrix of the system of linear equations. Then we use elementary row operations to reduce the augmented matrix to row echelon form. Then we write the new system of linear equations that corresponds to the augmented matrix in row echelon form. And finally, we solve the new system using back substitution. Now recall that linear systems may have a unique solution, no solution, or infinitely many solutions. We'll use Gaussian elimination to solve systems belonging to each of these cases. We'll start with case 1, linear systems with a unique solution. In example 3.2.8, we will finally solve that system B from page 70 that we noted was not easy to solve using back substitution. In example 3.2.8, we will solve system B using Gaussian elimination. The first step of Gaussian elimination is to write the augmented matrix of the system of linear equations. So step 1 is to write the augmented matrix of the linear system. So the first equation gives us the first row, 1, 2, minus 4, 8. The second equation gives us the second row, minus 1, 1, minus 2, minus 5. The third equation gives us the third row, 2, 6, minus 9, 9. That's step 1. That's the augmented matrix of the linear system. Step 2 is to use elementary row operations to reduce the augmented matrix to row echelon form. Now this augmented matrix is not in row echelon form. We have a bit of work to do. We want to transform it into an augmented matrix that is in row echelon form using elementary row operations. Now we know that we need at least these 3 entries in the bottom left corner to be 0 in order for an augmented matrix of this size to be in row echelon form. Let's start by performing an elementary row operation that will put a 0 in the position of that minus 1 in the second row. If I choose the elementary row operation row 2 plus row 1, I will get a 0 in that position. So the second row will become minus 1 plus 1, which is 0. Then 1 plus 2, which is 3. Minus 2 plus minus 4, which is minus 6. And minus 5 plus 8, which is 3. This is my new second row. I would also like to have a 0 in the position of this 2 in the bottom left corner of the augmented matrix. And so at the same time, I will perform a row operation to have that happen. I will perform the row operation row 3 minus 2 row 1. And so I have 2 minus 2 times 1, which is 0, the 0 I was looking for. 6 minus 2 times 2, 6 minus 4, that gives me 2. Next, minus 9 minus 2 times minus 4, that's minus 9 plus 8, which is minus 1. And finally, I have 9 minus 2 times 8, so 9 minus 16, which is minus 7. And the first row stays the same. 1, 2, minus 4, 8. So I've made quite a bit of progress already. I now am concerned with this 2. If this 2 was a 0, then the augmented matrix would already be in row echelon form. That 2 is not a 0 yet. And in fact, I'll start by performing an elementary row operation on row 2 so that this 3 becomes a 1, which is easier to deal with. So I'll perform the elementary row operation 1 over 3, row 2. Then the second row becomes 0, 1, minus 2, 1. The first and third rows remain unchanged. Now I'm still trying to put a 0 in the position of that 2. Now I can use the elementary row operation, row 3 minus 2 times row 2, to get in the third row 0 minus 2 times 0, that's still 0. 2 minus 2 times 1, that is 0, the 0 I've been looking for. Minus 1 minus 2 times minus 2, that is 3. And finally, minus 7 minus 2 times 1. Minus 7 minus 2, that is minus 9. The first two rows I haven't touched. I will copy those down. 1, 2, minus 4, 8, 0, 1, minus 2, 1. And this is now an augmented matrix in row echelon form. And so that concludes step 2. Step 3 is to write the new system of linear equations that corresponds to the augmented matrix in row echelon form. Let's do that. Step 3. What's the new linear system? X plus 2y minus 4z equals 8. That I get from the first row. From the second row, I get y minus 2z equals 1. And from the third row, I get 3z equals minus 9. This is my new equivalent linear system. Step 4 is to solve the new system using back substitution. Step 4, I'll number my 3 equations, 1, 2, 3. I'm starting with equation 3. 3z equals minus 9. I can solve for z. Z is equal to minus 3. Moving on to equation 2, y minus 2z equals 1. I have just found that z is equal to minus 3, so I'll use that to find y. Y minus 2 times minus 3 equals 1. Y plus 6 equals 1, and so y must be equal to minus 5. I am still looking for x, so I go to equation 1. X plus 2y minus 4z equals 8. I know y and I know z, so I have x plus 2 times minus 5 minus 4 times minus 3 equals 8. X minus 10 plus 12 equals 8, and so x is equal to 6. And so I've solved the system. Therefore, x, y, z, the solution to the system of linear equations, is 6 minus 5 minus 3. And so we found that the system has one solution, or a unique solution. It is therefore consistent. Remember that linear systems with one or infinitely many solutions are called consistent. Next, we'll look at case 2, linear systems with no solution.